Okay, let's move on to question 2 on homework from chapter 5 on simple horizontal curves. For this instance, we've got a surveyor who determined the intersection angle at 28 degrees. She also measured the external distance E, which is that distance from the PI to the highway center line, and found that to be 73.6 feet. So we're tasked to find 3 values: the tangent value, T, radius, R, and the degree of curvature, D sub C, in degrees, minutes, and whole seconds for the highway center line. So before starting on this problem, let's kind of remember what all of these things are, all these abbreviations. And a good place to look for that is onto your highway formula sheet for horizontal and vertical alignment. So at the top there, you've got this drawing for the simple curve. So the information that we were given in the problem was the intersection angle of intersection, and so that's down here as I, and remember that I is equal to delta. I is the same as that deflection angle for a simple horizontal curve, and that's that distance measured right here from the radius to the point of curvature, all the way along the radius to the point of tangency. It's also the same as this distance here up at the top of the curve, the angle that's formed between the forward tangent and the backward tangent. Okay, usually drawn right here to the right of the point of intersection. So those are the 2 pieces of information. That's one piece of information that was given to us. We're also given this E distance, this external distance, which is measured between the PI, that point of intersection, and the midline of our horizontal curve here. And remember that the horizontal curve starts at this point of curvature and extends all the way around until this point of tangency here. And the things that we're asked to find on that are the T, tangent distance, that is that distance from the point of curvature to the point of intersection, or from the point of intersection to that point of tangency. We're also asked to find the radius, which is a distance from the center to any point along that horizontal curve. So all these different lines that are drawn in here are just different instances of that same radius measurement from the center to any point along that curve. And then the last thing we're asked to find is the degree of curvature, which you won't see on this drawing, but if you remember, we talked about how that's defined in highways, that it's an arc definition, that here's your point of curvature and your point of tangency, that your degree of curvature is based on that 100-foot arc distance, and it's that angle that's formed between the 2 radii that have that 100-foot arc distance. We also discussed that how that changes things. If your radius is larger, your degree of curvature is going to be smaller. That's going to give you a flatter horizontal simple curve. And as your radius is smaller, your degree of curvature would be larger, which would give you a sharper curve. So that degree of curvature is going to make a difference to what your curve looks like in the end. So looking for those 3 values, given our formulas down here, we know we're going to need to find that degree of curvature. So that's one equation we're going to need to use. We know at some point we're going to have to find that tangent, and so that's defined here in terms of the radius, but we'll have to be able to find the radius to use that formula, and so here is our external distance defined in terms of the tangent. So we'll be able to work with these 3 equations, kind of backing through and finding the values that we need to find for this problem. So let's go ahead and remember what we're looking for again in this problem and what values we're given. So we're given that E value of 73.6 feet and that intersection angle of 28 degrees. So I'm going to go ahead and write those on my paper here. E is 73.6 feet and I of 28 degrees 0 minutes. Don't really need that, but we'll put it there. And we want to find T, R, and D sub C. So let's start off with that E equation from the formula sheet. That E is equal to T times the tangent of delta over 4. In this case, we know the E and we know the delta because remember I is equal to delta. So we need to find the T, so we need to do a little algebra here and rewrite that. So we'll say that T is equal to E over the tangent of delta over 4, and then plug some values in for that. We have 73.6 feet over the tangent of 28 over 4. And so putting that into the calculator, that gives us a value of 599.42 feet. We'll take that out 2 decimal places, as we usually do for solving these simple horizontal curve problems. So that's our first value. The second one, we'll go ahead and use that other relationship that involves tangent and radius. So T equals R times the tangent of delta over 2. Again, we know T now, we know delta, so we need to find that R, we need to rewrite. So we'll say that R is equal to T over the tangent of delta over 2. And so we'll plug our T value in that we arrived using the first formula, 599.42 feet over the tangent of 28 over 2. And putting that into the calculator gives us 2,404.14 feet. All right, so we've gotten a value for T, we've gotten a value for R. Now we're going to find our D sub C. Again, formula from the formula sheet. D sub C is equal to 18,000 over pi times R. In this case, we know our R now, so it's 18,000 over pi times 2,404.14 feet. And remember, for D sub C, we're going to want to take that out 5 decimal places. That's the degree of precision we're looking for here. And so when we do that, we wind up with 2.38321 degrees. But our answer is looking for that in degrees, minutes, and whole seconds. So we need to convert those decimal degrees into the degree, minute, second. I'm going to go ahead and just do that on my calculator. Since my calculator has a nice function to allow that to happen, I can put in this 2.38321, go up to this button that's right under the DEL, the degree, minute, second button, push that and scroll over to DMS, meaning degree, minute, second, hit the equal again, and that's going to convert my decimal degrees into degree, minute, second. So I have 2 degrees, 22 minutes, 59.56 seconds, but I want whole seconds, so that's going to have to round up. So 2 degrees, 22 minutes, 60 seconds. But again, 60 seconds is the same as a minute, so we'll go up 1 in the minute category. 2 degrees, 23 minutes, 0 seconds, or we can just call that 2 degrees and 23 minutes. So those are my final solutions then. The 599.42 feet for the tangent, 2,404.14 feet for the radius, and 2 degrees, 23 minutes for the D sub C.